Okay, so we've been talking about steels. Do these same things happen with different types of reservoir rocks? And the answer is yes, they certainly do. So here's a basalt. This is the classical case where we've taken a basalt sample. It's been immersed in water. The water has been in contact with supercritical CO2, so it's saturated with CO2. And what we see is we get calcite. These are calcium carbonate crystals, these sort of nice nodules that are forming on the surface. That's what we always typically see when we do these reactions in the laboratory. This case is one where we've taken a basalt sample and is just sitting in supercritical CO2 containing small amounts of water. It's never seen liquid water, just supercritical CO2. What we see is these minerals form. This is again a carbonate, a calcium carbonate, but look at the way that the structure is different. These are these kind of nodules that are forming on the surface. These are needles. And this is called aragonite. It's a slightly different crystal structure compared to calcite that's forming here. So we get chemically basically the same thing, but different crystal structures and different forms of the carbonates that get produced when we do reactions in aqueous versus supercritical CO2. So that, for us, that's really important because we really weren't worrying about this. Most people think about CO2 as essentially this inert gas. It's not going to drive reactions. We know now that that's just simply not true. As water gets picked up into that CO2, it does these same kind of reaction processes with at least reactive reservoir rock types. And it's not just basalt. It also works with, this is a dolomite, so it's a calcium magnesium carbonate type of sedimentary rock from a sample we've had from Texas. This is a test, again, taking that sample, just suspending it in supercritical CO2 with some SO2. And what we see in this particular case is that SO2 gets stripped in just hours out of that gas phase and forms gypsum, so calcium sulfate on the surface. So lots of reactions are taking place in supercritical CO2 that we just really didn't really know about as little as 18 months ago. So where this has gone is that the laboratory, so the national lab out here has invested about $15 million in developing some new instruments to look at these reactions. So no thermodynamic data, no kinetics data. We're starting essentially from scratch. We want to know what the water activity, what its role is, what the mechanisms, what the timescales are, and more importantly, can we get the data so we can now try to model this stuff? Because our reservoir simulators that we were showing you, so those subsurface simulations of that CO2 migration, they don't take into account any of this. They're not capable of doing it right now. So these new instruments will get that basic data so we can put those new capabilities into the next generation of reservoir simulators. And so they look like this, and these are, so it's a high pressure NMR, this is atomic force microscope, high pressure X-ray diffraction, and it's important enough so we have visitors like Department of Energy Secretary Chu. He comes by and we take him on a lab tour to go see these new instruments. So this is the last slide on this. I'm going to transition now to our pilot study to finish up here. But we're taking this information that we're getting from these new tools that you see here. This all gets fed now. At some point, it's going to get fed into these reservoir simulation calculations that we can do. And so this whole thing now fits together. And for me, I guess what the really interesting thing about these projects is that you really do have to work at these sort of just enormous changes in scale. You're talking about needing to understand molecular scale interactions with CO2, water, and host rocks, and then being able to use that in predictions that can span over many tens of kilometers in the subsurface. So that's really the interesting kind of challenge that we as engineers have to deal with.